In the last video, we started on this problem right here where we said, let omega be a complex cube root of unity, and omega cannot be equal to 1. And so we figured out what all of the complex cube roots of unity were. We figured out, well, we knew that 1 was one of them, and we used that to factor out this third degree equation right over here. And we figured out the other roots, cube roots of unity were -1 plus or minus the square root of 3I over 2. And we said, look, the problem said let omega be one of the, or be a complex cube root of unity. So I just picked it to be the negative version. So I said let omega be this thing right over here. Now, and just to kind of explore the space a little bit, we said, okay, what's omega squared? And we figured out that it was actually the conjugate of this. It's the plus version of this. So we got omega squared right over here. And then I kind of wasted your time a little bit because we know what omega cubed is. We know that omega is a cube root of unity. So omega cubed must be unity, but it wasn't harmful, I guess, to go through the process. It shows you sometimes my brain gets into a rut and just does stuff that it doesn't have to do. But we figured out, we multiplied this times omega to show that, hey, it is definitely equal to 1. So what we're able to do is set up a situation, and we will use this to think about the next part of the problem. So omega is equal to -1/2, or maybe I should say omega to the first power is equal to -1/2 minus the square root of 3 over 2I. Omega to the second power, let me write it over here. Omega to the second power is equal to -1 plus the square root of 3 over 2I. And then omega to the third power, and that was pretty straightforward, is equal to 1. And I touched on this in the last video. What is omega to the fourth power? Omega to the fourth power is going to be omega to the third times omega. So it's going to be omega again. So this is also going to be, let me scroll to the left a little bit. This is also going to be omega to the fourth power. Omega to the fourth power is the same thing as omega to the first power, which is this. Now what's to the fifth power? Well, it's going to be omega times the fourth power. So it's omega times this. Well, omega times this is the same thing as omega squared, so it's going to be that. So this is omega to the fifth power. And what's omega to the sixth power? Well, that's just the same thing as taking omega cubed and squaring it. So this is also going to be 1. So this is omega to the sixth. Or you could just view it's this times omega, right? Because it's to the fifth power, and we saw that that's also equal to 1. So we did set up, and the reason why I went up to the sixth power is because if you remember the old problem, we're rolling a die. And on that die, I'm assuming it's a normal 6-sided die, we're going to get values between 1 and 6. And we're going to take omega to the different powers, and we're going to see if it equals to 0. And we want to find the probability of this being equal to 0. So let me write this down. We want to find the probability. That omega, and we're just using the omega that we picked, because they said it's one of the complex roots that isn't 1. So we want to find the probability that omega to the first die of the roll plus omega to the second die of the roll plus omega to the third die of the roll, that when you take their sum, that is equal to 0. This is what we need to figure out. So to figure this out, let's just figure out what combinations of powers of omega will even add up to 0. How can we even add them up to 0? None of these, I mean, they all have to cancel out some way. And if you look at them, it looks pretty interesting of how they might cancel out. If I take one version of this, the only way that they really can cancel out is if I take one version of this and add it to this, and then add it to this. Let me show you. If I take -1/2 minus square root of 3 over 2I, and I add it to this, -1/2 plus square root of 3 over 2I, and then I add it to 1, and then I add it to this, and then I add it to this, what do I get? Well, you're going to have this guy and this guy are going to cancel out. -1/2 plus -1/2 are going to be equal to -1. You add -1 to 1, it's going to be equal to 0. So essentially, what we're going to say, what it's asking us, what's the probability that I get for each of these terms, that I get 1 each of these powers of omega? Or another way of thinking about this, what's the probability? So if we think of it this way, so R1, let's think of it this way. R1 could be equal to we could get, if we say that this is going to, we're going to get omega here, we're going to get, which is the same thing as omega to the fourth power. So this is, could be, R1 could be 1 or 4. R2, and this is in the situation where the first one gives us omega, the second one's omega squared, or the second one gives us this value, and then the third one gives us 1. So R2 would be 5 or 2. R2 would be 5 or 2. And then R3 would be equal to, R3 would be equal to 3 or 6. 3 or 6. Now, I want to be very clear. We could swap these around. There's actually six ways that you could instead of this being the first roll, this roll could be 1 or 4, and then this one could be 5 or 2, and then this one could be 3 or 6. So there's actually 6 ways of doing this. I guess you could say you could permute these six different ways, or 3 times 2 times 1. But we'll think about that in a second. But let's just, assuming that we want this way, where this first one is going to evaluate to this, and the second one is going to evaluate to this, and the third one is going to evaluate to this. What's the probability of that happening? And then we're going to multiply that by 6, because there's 6 ways to rearrange these terms right over here. So let's do that. So what's the probability of that happening? Well, the probability that R1 is a 1 or a 4, well, that's 2 values out of 6, so the probability is 1/3 there. The probability that R2 is a 5 or a 2, well, that's also going to be 1/3. That's 2 values out of a possible of 6. The probability that R3 is a 3 or a 6, only 2 possibilities there. So 2 out of 6 possible faces of the die, so times 1/3. So the probability that this first one is going to evaluate, to this value right over here. The second one's going to evaluate to this value, and the third one's going to evaluate to 1, is going to be 1/3 times 1/3 times 1/3, which is 1 over 27. Now, let me be, and I touched on this already. There's 6 ways that you could rearrange this 6 ways. You have 3 terms, and you're putting them in 3 places. So in the first place, you could put 3 of the terms. In the second place, you have 2 terms left that you could put. And in the last place, you only have 1 term left. So there's 3 times 2 times 1 ways to arrange these things. We can arrange this 3 times 2 times 1 different ways. So there's 6 different arrangements. The probability of each is 1 over 27. So the probability under question, this thing over here, there's 6 arrangements. There's 6 arrangements of getting these things to be added up in this way. And the probability of each of them is 1 over 27. So it's equal to 6 over 27. And if you divide the numerator and the denominator by 3, it's equal to 2 over 9. And we're done. It wasn't too bad, I think. The probability of getting omega to the R1 plus omega to the R2 plus omega to the R3, where R1 and R2, R3 are numbers obtained from rolling a fair die. The probability that when you add all of these, it's going to be equal to 0 is 2 over 9. Anyway, I thought that was a pretty neat problem.